Are black holes really just giant cosmic vacuum cleaners? Thanks to Hollywood blockbusters, we kind of picture them as these massive, terrifying drains in the fabric of space, just relentlessly sucking up everything in the universe until absolutely nothing is left. It's a great plot device for sure, but is it scientifically accurate? Let's dismantle that myth today and uncover the actual mechanics behind these dark centers of gravity.
Section 1. A stellar tug-of-war, the balance that keeps stars alive.
Okay, let's dive right into this by rewinding the clock a bit. Because to understand a black hole, we first have to understand the entity that creates it, a living star. You see, a black hole doesn't just poof into existence out of nowhere. It's the final dramatic chapter in the biography of a massive star. And throughout its life, a star is locked in this delicate, literal, billions of years-long tug-of-war. Right at the core, you have continuous nuclear fusion reactions happening. This is the star burning its fuel, like hydrogen or helium, which produces massive amounts of heat and light. And that creates a powerful outward force. But pulling against it is an equally powerful inward force, the star's immense gravitational pull. As long as those two forces are perfectly equal, the star maintains its equilibrium. It stays alive and intact.
Section 2. The cosmic life cycle, when the fuel runs out.
But just like a car speeding down the highway, a star's fuel doesn't last forever, right? Eventually, that hydrogen or helium gets completely burned up, and when that happens, the entire equilibrium of our stellar tug-of-war is just shattered. Here's the dramatic falling action of a massive star's life. Step 1. The nuclear fuel depletes, meaning that vital outward force of heat and energy suddenly stops. Step 2. With absolutely nothing to push back, the inward force of gravity completely takes over. For a sufficiently massive star, this causes it to violently collapse in on itself, leading to Step 3, a spectacular supernova explosion. And finally, Step 4, a tiny, incredibly dense core is left behind, and it just keeps collapsing inward under its own uncountered gravity.
Section 3. The Rule and the Scale, the Chandrasekhar Limit.
Now hold on, before you start worrying about our own sun collapsing into a black hole and swallowing the Earth, let me reassure you, our sun is entirely safe. Not every star actually gets to become a black hole. There's a very specific threshold required for a star to face this extreme kind of collapse, and that threshold is determined by a number, 1.4. This is the Chandrasekhar limit, named after the brilliant astrophysicist Supermanand Chandrasekhar. He proved that for a dying star's core to even potentially become a black hole, it has to be massive enough to exceed roughly 1.4 times the mass of our own sun. If it's smaller than that limit, like our sun is, it ends up becoming a white dwarf or a neutron star. It totally escapes the fate of becoming a black hole.
But for those truly massive stars that do cross the limit and collapse into a stellar black hole, the scale of their density is literally mind-bending. Consider this number, 50. If a star with the exact mass of our sun were somehow compressed into a black hole, all of that immense mass would be packed into a tiny sphere just 50 kilometers in diameter. Think about that for a second. Imagine taking something 330,000 times heavier than the Earth and squishing it down to the size of a single city. That is the intense reality of black hole density.
Section 4. Seeing the invisible, spotting dark centers of gravity.
So, if a black hole has such immense density and such an overpowering gravitational pull that literally not even light can escape its grasp, it brings up a really fascinating question. If light can't escape them, making them completely invisible dark centers of gravity, how do scientists actually find and study them? Well, the answer lies in the accretion disk. While the black hole itself is completely invisible to us, it doesn't just exist in a vacuum. It interacts violently with its neighborhood. The accretion disk is this massive, glowing ring of gaseous matter, dust, and debris that gets pulled in by the black hole's gravity, and it revolves around that invisible center at absolute extreme speeds.
Let's walk through exactly how this highly visible ring comes to be. First, the black hole's gravity aggressively pulls in nearby gas and stellar debris. Second, as this matter gets closer, it starts revolving at incredibly high speeds, kind of like planets orbiting a star, but way, way faster. Third, because it's moving so fast, the debris violently rubs together, It compresses and heats up to literally millions of degrees Celsius. It basically turns into a flowing, fluid-like fire. And finally, these intensely hot, glowing particles emit electromagnetic radiation, specifically powerful X-rays. So we don't actually see the black hole itself, we see the fiery disk of friction surrounding it thanks to those X-rays.
And here's a super cool detail you might have noticed if you've ever looked at real imagery of a black hole. One side of the accretion disk always looks way brighter than the other. Why is that? Well, it's due to something called the Doppler beaming effect. Because the disk is spinning so incredibly fast, the glowing particles that are spinning toward our perspective on Earth actually appear brighter to us, while the particles spinning away from us appear dimmer. It's exactly how scientists are able to interpret the rotation of these cosmic objects from millions of light years away.
Section 5. Millions in our galaxy. The reality of cosmic neighbors.
Now let's zoom out to the macro view and consider our own cosmic neighborhood. When we talk about phenomena this massive and destructive, it's super easy to assume they're incredibly rare, right? Like maybe there's just one or two hiding in the deepest, darkest corners of the universe. But the reality is way more surprising. Scientists estimate there are between 10 million to 1 billion stellar black holes right here in our own Milky Way galaxy. They are, by far, the most common type of black hole in existence. The sheer volume of these objects just floating around in our galactic backyard is absolutely staggering.
Which brings us right back to our original question and completely busts that whole cosmic vacuum cleaner myth. I mean, if there are up to 1 billion black holes in our galaxy alone, why hasn't everything been sucked up? Well, because black holes simply act as extremely heavy gravitational centers. Just like planets safely revolve around the sun, planetary bodies and stars can revolve perfectly safely around a black hole. The source material notes it best, if you maintain a proper distance, you will be safe and secure. It's literally just a matter of cosmic social distancing. As long as you don't cross that point of no return, a black hole is really just another neighbor in the galaxy.
So, we've learned today that stellar black holes are the most common type out there, born from dying stars balancing extreme forces of fusion and gravity. And while they absolutely hold immense power, they just aren't the mindless destroyers that pop culture makes them out to be. Which leaves us with a final, provocative thought. If black holes aren't the terrifying vacuums we always thought they were, what other cosmic phenomena out there in the deep universe are we completely misunderstanding? Keep questioning, keep learning,